Hi everybody, welcome back. We're going to continue to take a look at double integrals and polar coordinates. And this video we're just going to look at a couple of examples. So the first example is here: find the volume of a solid formed by the surface z equals the square root of 16 minus x squared minus y squared inside the cylinder x squared plus y squared equals 4. So first let's take a look at what this solid looks like. So here's the solid, here's the surface, z equals the square root of 16 minus x squared plus minus y squared. But here's just the part of the surface at the top of this cylinder, x squared plus y squared equals 4. So here's the cylinder, here's where it connects right here. That's the solid itself. Now this surface is actually a hemisphere. So if we look at, if I extend everything, here's the hemisphere, and there you can see the cylinder poking out. This is the surface square root of 16 minus x squared minus y squared. It's just the top half of the sphere. And I only want to look at the part that's inside of this cylinder, x squared plus y squared equals 4. So I've just gone ahead and trimmed everything up, and that's how I get this solid here. Now for this problem you might think, well, do I have to find this intersection? Do I have to find a curve that describes where these two things intersect? Not in this case, because in this case, if we want to find the volume, we're just integrating this surface over the appropriate domain. And the domain that we need is the inside of the cylinder x squared plus y squared equals 4. So it's inside of this disk of radius 2. So we don't need to worry about where these things intersect. I'm just going to integrate a function that describes the surface over the disk. So you can think of just projecting the domain of integration is just looking at this from straight above, projecting this into the xy plane. So that's all I need there. So going back, this is kind of what I just said. I'm going to integrate this surface, this hemisphere, just the piece that's above this disk that's centered at the origin of radius 2. So it's easy to describe this disk in polar coordinates, because inside this disk the radius is just going from 0 to 2 all the way around, and since we're going all the way around, theta goes from 0 to 2 pi. So easy bounds for my my integral in polar coordinates. I need to rewrite this surface in polar coordinates, so you can think that x squared plus y squared is r squared. So if I just factor this negative out, that's minus x squared plus y squared. So this surface in polar coordinates is the square root of 16 minus r squared. You could also plug in r cosine for x and r sine for y and simplify to get r squared as well, because then you could factor out a negative r squared and you'd be left with cosine squared theta plus sine squared theta, which is 1. So that works as well. Either way you do it, this is the surface that you get in polar coordinates. Now when I set up this integral, again, here are my bounds. In theta, I'm going from 0 to 2 pi. In r, I'm going from 0 to 2. Here's my function. Don't forget, we need to multiply by r. So I have this r I need to multiply my function by, dr d theta. Now, since my bounds are just numbers, I don't have any variables in my bounds. And my function here is completely in terms of r. I don't have any thetas. I could think of multiplying by a 1 to be a function of theta. This is a separable integral. We talked about this in section 15.1. If you have a function that you're integrating that can be written as a function of one variable times a function of the other variable, and there are no variables in your bounds, you can completely separate the integral. So that's what I'm going to do here. You don't have to do this. You could just go through and integrate as we always do. But in this case, I'm going to go ahead and separate things. So instead of a double integral, I have a product of two single integrals. So here's just the integral in theta, which is just integrating 1, and here's the integral in r, which is this function. Now here this is going to be easy. I'm just integrating 1, so it's the length of this interval, so it's just 2 pi. This integral is more involved. I need to do a u substitution, let u equal 16 minus r squared. Then my du is going to be negative 2r dr. And I have the r here. I'm missing the negative 2, so I need to multiply and divide by negative 2. So you can see in this next step, I've integrated, I've gotten theta from 0 to 2 pi. I've multiplied by negative 2 to get the part of dr that I was missing, or sorry, du that I was missing. And I also need to multiply by negative 1/2, so that really I haven't changed the integral, I'm just multiplying by 1. Okay, so now this negative 2r is going to go with dr to become du. I've rewritten the square root as 16 minus r squared to the 1/2. I'm ready to integrate. So when I integrate, and here I'm just evaluating this first part, that's just going to be 2 pi. When I integrate, this negative 1/2 was outside, so that's just sitting there. The negative 2r goes with the dr, becomes du, it goes away. And now I just need to integrate this term, so I add 1 to this exponent. It becomes 3/2. I divide by the new exponent, which is the same as multiplying by 2/3. So that's what I get when I integrate and I evaluate from 0 to 2. Now I'm going to go ahead, simplify this. This becomes negative 1/3, and I'm going to factor that negative 1/3 out. So I have this 2 pi sitting here. I'm also going to think of this negative 1/3 as being outside of what I'm evaluating. I'm going to plug in 2 here, and I get 16 minus 4 to the 3/2. Minus, I plug in 0, I just get 16 to the 3/2. Right? And so if I write everything out, I multiply these together, I get negative 2 pi over 3, 12 to the 3/2, minus 16 to the 3/2. Now, I just multiply everything by a negative, so distribute this negative through to switch the order of subtraction, and I'm going to write out what it means to have something to the 3/2 power. It's just that number times the square root of that number. So 16 to the 3/2 is really 16 squared root of 16, and then 12 to the 3/2 I have minus 12 times the square root of 12. But the square root of 16 is 4, so 16 times 4 is 64. The square root of 12 is 2 times the square root of 3, so 12 square root of 12 is really 24 square root of 3. And now one more thing I can do is factor an 8 out of this. So if I factor an 8 out of this, 2 pi over 3 becomes 16 pi over 3, and this difference becomes 8 minus 3 root 3. And that's my answer. Now practically for a problem like this, you could have stopped here. Right here, that's a perfectly good answer. But I just did some simplifications. And that's the end of that problem. So all of the examples we've looked at in this section have been over polar rectangles, meaning that all of the bounds have been numbers. But that doesn't always have to be the case. We can integrate over more complicated regions, where you get functions in the bounds. So our next example says, find the area enclosed by the graph of r equals 3 cosine 3 theta. So first we should try to graph this. So how can you plot this function? Well, go back to when you first learned how to graph functions. What did you do? Most likely you made a table. And so you started plugging in numbers for the independent variable and see what the dependent variable had to be. So we could do the same thing here. Plug in values for theta, which we know the values for cosine. So if I plug in 0 for theta, I'm going to get 3 times cosine 0, which gives me 3. If I plug in pi over 6, that's going to be cosine of pi over 2, which is 0. And you can keep doing that. If I plug in pi over 3, I get negative 3. If I plug in pi over 2, I get 0. And you can keep going, you can keep going. But now you have to plot these points and think of them in terms of polar coordinates, so a radius and an angle. So if I want to plot the point 0, 3, that means I'm at an angle of 0, which is the positive x-axis, and I'm 3 away from the origin. So that's this point here. Angle of 0 and 3 away. Now an angle of pi over 6, you can see I've tried to draw it here. There's an angle of pi over 6. My radius is 0, so I'm at the origin. So I've gone from 3, 0 in x, y coordinates, but an angle of 0, radius of 3, down to the origin when my angle gets to be pi over 6. So I've just tried to connect those with this line. Then if I plug in pi over 3, I got negative 3. So this is our first encounter with a negative radius. So what does that mean? That means instead of going in the direction of your angle, pi over 3, I go in the opposite direction. So at pi over 3, instead of going 3 in this direction, I go 3 in the opposite direction. And so this is negative 3 for r, pi over 3 for my angle. So now I've drawn all the way to here. Once I get to pi over 2, I'm 0 again. So I come back to the origin. If you keep going around, if you plug in 2 pi over 3, you would get 3. If you plug in 5 pi over 6, you get 0. And if you plug in pi, you would get negative 3, and you'd be back here. So it traces out this curve. Okay, so now I want to find the area. Remember, in polar coordinates, area is r dr d theta. I need my bounds. To find the bounds for r, I want to find the area inside this curve. So r is always going to go from the origin to the curve itself. So r is always going to go from 0, and the curve is described by 3 cosine 3 theta. So you can see now I have variables in my bounds of integration. So for r, I'm going from 0 to 3 cosine 3 theta, and for theta, I'm going from 0 to pi. Why am I going from 0 to pi? Well, I want the area inside this curve, so I need to go around this curve once. And as I go through this, right, when I got to pi, I was back where I started. So when theta is pi, I've gone around the curve once. If I integrated from 0 to 2 pi, I'd be going around this curve twice, and I would get twice the area that I need. Okay? So this is the integral you need to evaluate. Integrate r from 0 to 3 cosine 3 theta, and then integrate theta from 0 to pi. So that's one way to do it. Another way to do it is I can find the area over this entire curve, or this is what they call a rose graph, and it has 3 petals. They're all the same area. Now, it might not be clear the way that I've graphed it, so let's take a look at a better graph. Here's the same curve, right? So these 3 petals all have the same area. So I could just find the area of one of these petals and then multiply by 3. And I don't have to integrate over the entire curve, just one of these petals. So if I do that, that's exactly what I'm going to do. Integrate over one of the petals, multiply by 3. So there's the 3. Now I just need to figure out what the bounds for this petal are going to be. And so my r bounds don't change. I'm still going from 0 to the edge of the curve. I'm still going to integrate r. I need to think of the theta bounds. So if I want to find the area of this petal, I need to think of where is theta starting at this petal and where is theta stopping. Well, one angle, it's definitely starting at pi over 6. It's stopping at pi over 6. And it's the same angle, just on the opposite side of the x-axis. So that's negative pi over 6. So my theta bounds are going to be from negative pi over 6 to pi over 6, because this petal occurs between the angles of negative pi over 6 and pi over 6. And now you might say, well, isn't this also 11 pi over 6? Why can't I integrate from pi over 6 to 11 pi over 6? Well, this brings up something we haven't talked about yet, because when you're integrating with respect to theta, or you integrate in general, you usually go from the smaller number to the larger number. And as theta increases, we're going around the xy plane counterclockwise. So if I integrate from pi over 6 to 11 pi over 6, I'm going all the way around. And I'm not going to get the area of one petal. I'm actually going to get the area of 5 petals. Why is that the case? Well, if I integrate from pi over 6 to pi over 2, I'm going to get the area of this petal. From pi over 2 to 5 pi over 6, I get the area of this petal. From 5 pi over 6 to 7 pi over 6, I get the area of this petal. That's the entire graph. From 7 pi over 6 to 3 pi over 2, I get the area of this petal again. And then from 3 pi over 2 to 11 pi over 6, I get the area of this petal again. So you would get 5 petals. And so then you may ask yourself, well, instead of negative pi over 6 to pi over 6, can I just integrate from pi over 6 to pi over 2? Or can I integrate from pi over 2 to 5 pi over 6? Sure, that's fine. There are many ways to get this area. This is not the only way to set up this integral. There are several ways to do it. But this is the way I've set it up, so let's just go ahead and evaluate this integral. All right, so first we're going to integrate with respect to r to get 1/2 r squared, and then plug in our bounds. The 0 doesn't matter, but when I plug in 3 cosine 3 theta, I have to square that. So I end up with 9 cosine squared 3 theta, and I have the 1/2 there. So now I have this integral in theta. I have a cosine squared again. We dealt with that in the last video. We plugged in 1/2 plus 1/2 2 theta. But when I use that trig identity, I have to double whatever the argument of cosine is. So whatever I'm taking cosine of, I have to double. So in this case, I replace cosine squared 3 theta with 1/2 plus 1/2 cosine 6 theta. Whatever I'm taking cosine of gets doubled. So that's using that trig identity. Now I'm going to go ahead and factor out some constants. So I'm going to factor out this 9/2, bring it outside the integral. I'm going to factor out a 1/2, also bring that outside the integral. And that leaves me with a 27/4 sitting outside this integral. And what am I integrating? 1 plus cosine 6 theta. I integrate 1 to get theta. I integrate cosine to get sine. And I have to divide by this constant. So I get 1/6 sine 6 theta. Again, you can write out the u substitution if you like. And now I evaluate from negative pi over 6 to pi over 6. I plug in my bounds. I plug in pi over 6. I get pi over 6 plus 1/6 sine pi. I plug in negative pi over 6, get minus negative pi over 6, minus 1/6 sine of negative pi. These signs both go away. They're both 0. Pi over 6 minus negative pi over 6 is pi over 3. or 2 pi over 6, I multiply to get 9 pi over 4. Okay. And that's your answer. That's the area enclosed by this curve, because I already multiplied by the 3 out here. So 3 pi over 4 would be the area of one petal. So now you might be asking yourself, hey, when I got here, I'm integrating an even function with respect to a symmetric domain. Can I change these things? Can I multiply by 2 and change this lower bound to a 0? Sure. And now some of you might be noticing, well, you know what's better than just finding the area of one petal? This is a symmetric domain in X. Can I just find the area of half a petal and multiply by 6? Absolutely. I could have started this integral, at least at this point. Instead of multiplying by 3 here, I could have multiplied by 6 and set up my bounds in theta going from 0 to pi over 6. If theta goes from 0 to pi over 6, I'm just getting this half petal here. And all of these petals are the same size, so then 6 halves is going to give me the entire area. Like I said, there are many ways to set up this integral. You can try them out if you're interested and you have time. You should always get 9 pi over 4 if you set up the integral correctly. Alright, so that's it for double integrals and polar coordinates. In the next section, we're going to jump back to chapter 16 and go over one of the most important results in this course and talk about Green's theorem.